These next kind of differential equations are called exact equations. Now, I'm going to split this up into two videos. The first one's going to be kind of going through the what's what, and I'm going to try to make this familiar to something that you learned in Calc 3. And then in the second video, I'm going to do a bunch of examples, okay? So sort of hold on through this first one. I'm going to go hopefully slow enough and try to bring back some of those things that we learned before. So here we go. We want to solve the following differential equation. Now it looks like 2xy minus 9x squared dx plus 2y plus x squared plus 1 dy equals 0. Now this is really just a fancy way of kind of saying if you multiply everyone by dy dx, or by dx, sorry, not multiply, divide everyone by dx, you end up getting this thing plus this thing dy dx equals 0. So this is just another way of looking at that equation. Now let me start by giving us the answer, okay? Or at least part of it. Let's take the function f of xy equals y squared plus x squared plus 1y minus 3x cubed. Now our goal by the end of this will be to actually produce this function, but for now, let's just assume that we have it. So what I want to find fx and fy. So the partial derivative of f with respect to x, so the y squared goes away. The next one is just 2xy minus 9x cubed. 9x squared because you subtract 1. Fy is, okay, I take the derivative of this thing with respect to y, and I get 2y plus x squared plus 1. Okay, do those things look familiar? Yeah, they look like this and this. So what does this mean? This means that our equation up here, given this function f, looks like fx dx plus fy dy. Now that should look familiar to us because it looks like the total differential, which is if we have a function z equals f of xy, then dz is fx dx plus fy dy. And so in this equation, we're saying that dz is equal to 0 for every x and y, which means we must have the function f of xy equals a constant. And so the implicit solution to our differential equation is f of xy is equal to c. Okay, so this is going to be our solution to the differential equation once we have produced this f here. Okay, so once we have produced this function f, then I know what I'm saying here is that the solution to this differential equation is y squared plus x squared plus 1y minus 3x cubed equals a constant. So that's what I'm saying here. All right, now I want to define some terms and talk about how to get the f. So the differential equation, m of xy plus n of xy dy dx, or equivalently m dx plus n dy, is called exact in a rectangle R if there's a function f of xy such that fx equals m of xy and fy equals n of xy. Okay, so that's what we just did. So if I can find a function such that the partial derivative with respect to x is the m thing, and the partial derivative with respect to y is called the n thing, then we call it exact, right? And that's its name. All right, let's take a trip down memory lane for a minute. Okay, so here's our trip down memory lane. A vector field G equals mi plus nj, otherwise mn with the angle brackets, is called conservative if what? It is the gradient of a vector valued function f. That is, if there exists a function f so that the gradient of f is g, meaning the gradient of f is fx fy, which is mn. And so what this means is that this thing is conservative if you can find a function f so that fx is m and fy is n. That's what we just said. That's literally the exact same thing as we wrote here, but we did it in sort of different terms. And then the f function in this case was called the potential function. And so what it should feel like to you is that this section we're going to be finding the potential function. Okay, now here's, I want to do this so that you can remember stuff, okay? Knowing the potential function is what made line integrals so much easier in the fundamental theorem of calculus for line integrals. And so when we did those way back then, we actually, went through some work to find that potential function. Okay, next thing here. So, Clairaut's or Clairaut's theorem, I don't know which one it is. If f of x is defined on a disk D that contains the point AB, and if fxy and fyx are continuous, then, okay, all you basically remember from this thing is that, oh, by the way, fxy is equal to fyx with some fine print about being continuous in the rectangle. All right, well, most of the functions that we deal with in the rectangles are continuous. So the way you remember this is that you can take partials in any order you want to. Okay, here we go. The last thing is the test for a vector field being conservative or not. So we had the definition of when it was conservative, but here we go. So the test was, let G being this vector field over a nice region, all this kind of stuff. If my equals nx, then G is conservative. Okay. So roughly speaking, what is going on here? I'm going to use some of this space down here because I'm going to draw a picture that I want you to sort of keep in your head. So here is the f function. We take the partial derivative with respect to x and we get m. We take the partial derivative with respect to y and we get n. Then for m, we take the partial derivative with respect to y, and you get my, which is, oh, by the way, fxy. Then for n, we take the derivative with respect to x, and we get nx, which is, oh, by the way, fyx. So what we're saying here, look at this. fxy and fyx we know are equal. So the test for being exact really comes from my equals nx is really just saying, oh yeah, these things are the same because they would have been provided this f exists. Okay? So this is kind of how I think of this. M comes from the derivative with respect to x, and then you take a derivative with respect to y to get down to here. To get n, you take a derivative with respect to y, and then we take a derivative with respect to x to check it to see if it's exact or not. Now, you might think, like, why do I need this? Well, give me a couple examples and I will explain. Okay? All right. So back to the thing that we are doing here, because I don't have to do anything with this. This is the same in both classes. So if G is this thing, is this vector field conservative? If so, find the potential function. All right. Well, how do we do that? Well, to test to see if it is conservative, what we'll do is this is m and this is n. Let me change colors. There's a lot of green on this page. I will find my, and my is simply 2x. Okay, well, that's it. And then nx is just 2x. Oh, look, those are the same. Okay, so yes, it is conservative. Check. Okay, then how do we find the potential function? So what we have discovered is that we have the m and we have the n. We took this derivative to get this thing, we took this derivative to get this thing, and those were equal. All right, well, what I want to do is I want to take this thing and sort of go back up to f. Now, I also want to say that there's not just one way to do this. I'm just showing you my way. If you have another way that you like to use better, then go right ahead. So what I'm going to say is that f is the antiderivative of m with respect to x, which is the antiderivative of 2xy minus 9x squared dx. Okay, so we take an antiderivative, and we get x squared y minus 3x cubed plus a constant. But that constant, because we're in partial antiderivative land, that constant is simply any function of y. So I'm going to call it plus little g of y, h of y, whatever you want to call it. So this is my new potential f function here, right? This is my new thing for what I think f is. And what I've just done is I've taken this and I've sort of ridden the elevator back up. And what I'm going to do is I'm going to take the elevator back down to n. All right, so then what is fy? Well, fy is x squared plus g prime of y. And fy is supposed to equal n, and n is equal to 2y plus x squared plus 1. So I have x squared on both sides, so what is g prime? Well, g prime of y is 2y plus 1. So that means that the little g function is y squared plus y. Okay, and now we're good to go. I can take that thing and plug it back in, and I have my potential function being x squared y minus 3x cubed plus y squared plus y. And I could maybe simplify that a little bit. I could put this y squared in front. I could put the 3x cubed in the back, and I could take this y and factor it out as x squared plus 1y. Okay, and now you see, look at that thing right there. Where did that come from? Let me spin back a couple pages, or just one page. That was this function right here. All right. So what we've done is I've defined what exact ODEs are, and I've more or less said that the way we're going to solve these things is by doing the exact same thing that we did back in Calc 3 with potential functions and conservative vector fields. So let's do the same exact example right here, okay? So test for exactness here. So the first partial derivatives of m and n are continuous in a rectangle R, then the equation, this thing, is exact if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. All right? And what I'm saying here is that this is all the exact same thing. So fxy is my, fyx is nx. All of this is the same as it was before. So when I want to solve this equation right here, what I need to do is, okay, that's m and that's n. I will first verify what is my. Well, my is 2x and x is 2x. And from that very first page, it means that the solution to this thing is f of x y equals c, which is y squared plus x squared plus 1y minus 3x cubed equals a constant c. So we're just going one step further than we went before in the potential function conservative vector field discussion. Okay, hopefully that video was enough to get us through the ideas for what's going on here. And in the next video, we will do a bunch of examples. And I'll see you then.